So thanks everyone for joining. And today we are going to learn all about water. So we're hearing from Larry Band from University of Virginia and Claire Welty from University of Maryland, Baltimore County, going to be tag teaming a presentation on water and water quality from the theme team that BSEC has on this topic. So I hand it over to Larry and Claire. Why don't you guys take it away?
Okay, well, thanks. I'm going to go first, followed by Larry today. So we have three co-chairs of the theme team, the water and water quality theme teams. You're hearing from two of them today. And so today we're going to touch a bit on some of the hydrologic modeling approaches that we're using in this project. So let's see, why is this not going? Okay, so some example water and water quality theme team questions that can be addressed with modeling. We have lots of lists of questions, both basic science questions and translational science questions. So an example of a basic science question that we could potentially address with modeling is, what are the sources and flow paths and urban drainage systems that can deliver runoff, nutrients, sediment, and contaminants to streams? On the translational side, an example kind of question is, how do combinations of gray, green, and blue infrastructure mitigate stormwater and water quality hazards? And moreover, how can they be designed to improve environmental equity? So these are just example kinds of questions to give you an idea of the flavor of the kinds of things that we're talking about. So the hydrologic models being used in this project that we know about so far are as follows. And these are terrestrial hydrologic models. You'll be hearing about atmospheric models from other folks. So the first one that's being used is the EPA stormwater management model. This has been around for about 50 years. First was released in 1971. It's basically a pipe flow model. Well, it started out as a pipe flow model. Those are the strengths of the model. So it's a hydraulic pipe flow model. And since, it's evolved over time to have hydrologic components involved or tacked on as well. So our experts in this area are James Hunter at Morgan State and his students, and Shirley Clark at Penn State and her students, and there are likely other folks that are also using this in their work. But on our current team, those are the two kind of leads that we know about. A newer model that is being tested out at Morgan State is this model called CityCat, the City Catchment Analysis Tool. And this is being checked out and tried by Julia Atayi, who is a PhD student working with James at Morgan State. And this model solves the 2D shallow water equations. The purpose of the use of this model is to assess hazards from pluvial and fluvial flooding. So we're really excited about Julia testing this out because we know that street flooding or pluvial flooding is a problem in many parts of Baltimore City. So we're excited about this and look forward to seeing some results in the future. So we're not going to talk in detail about these first two models today. So the second two are what we're going to give you some details on. We're hoping to hear about these other models in the future. So the next model we would like to mention is ParFlow, which is what started off as a groundwater model. I'll give you some more details in a minute. So it's a coupled groundwater surface water model, coupled with a land surface model, and then EcoSlim is an effective transport model. And I'm going to be talking about that in detail. And then finally, RESIS is a regional hydrologic eco-simulation system model that looks at coupled water, carbon, and nutrient cycling. All these models can be applied at any scale. Sometimes there are practical limitations on the scale you can apply them to owing to memory effects and whatnot. So they all have, pluses and minuses, and they're all used for different purposes. So I'm going to go ahead and talk about ParFlow, and I'm just going to give some examples of how we applied it in the past, and then Larry's going to follow up and talk about some RESIS applications. And the idea is to give you a flavor of how these models have been applied. And I'm only picking a couple. I can't go through many examples of ones that we've done from our shop here, just to give you the flavor. Okay, so ParFlow originated at Lawrence Livermore National Lab, and the PAR comes from parallel processing. And so it was originally a purely groundwater flow model, similar to ModFlow for the U.S. Geological Survey. And then Reed Maxwell has taken the model way forward. The current keepers of the model are Lawrence Livermore National Lab and Reed Maxwell and his group at Princeton. So now the model is coupled with the capability to model surface water flow through boundary condition specification, and is coupled with the community land model for incorporating meteorologic forcing. So so just talking about some of the inputs here. So the model requires meteorologic forcing, precipitation, temperature, solar radiation, and wind speed, and we use NLDOS data, the North American Land Data Assimilation System, as that data source, widely available publicly. And then also the model requires land cover. So we need some idea of the pixelation of vegetated cover, and we alternate between using the USGS 30-meter land cover data, and sometimes we use a Chesapeake Conservancy 1-meter land cover data, depending on what we're doing. And so the land cover heterogeneity is what's going to, coupled with the meteorologic forcing, is what's going to affect evapotranspiration, right? So from the community land model, we generate the upper boundary conditions that go into par flow. So the precipitation and evapotranspiration are generated by the community land model. So meanwhile, what you have to specify in par flow, the other inputs that are not necessarily changing, as is topography, soil and rock permeability and porosity, the location of the bedrock saprolite interface, if that's relevant, and aquifers and aquitars, if that's relevant. And then you can also specify anthropogenic perturbations. You can tweak the model with anthropogenic perturbations, such as recharge from leaking potable water pipes and others. So all of this goes into par flow coupled with the boundary conditions. And what is solved for is pressure head and saturation. So the par flow is variably saturated, is a three-dimensional finite difference code, variable saturation. So basically, the degree of saturation can be from 0 to 1 at any cell. And so there's a natural fluctuation as you have infiltration and drainage of the pressure head and saturation. And there's no external specifications. Oh, the water table must stay here. So the water table will rise and fall with infiltration and evapotranspiration, taken infiltration in, evaporation, ET out. So of course, from these variables, you can generate the soil moisture state, if that's of interest to you, and that will feed back into the community land model as the state of the soil that of course is going to affect evapotranspiration. The outputs that we're interested in for post-processing from pressure head and saturation are aquifer levels, depths of groundwater, groundwater velocities, which we can use for other kind of calculations, and this should say stream flow. The flow got sawed off by somehow. So stream flow. So volumetric flow rate in the stream is one of the outputs we can post-process from this model. So that's the modeling basis. This can be applied at any scale, any pixelation. Reed Maxwell has applied this whole coterminous United States. We've been looking at smaller watersheds, and we've tried to adapt this for urban applications in the work we've been doing here. So I'm going to give you 3 examples of applications. The first example was led by Aditi Bhaskar, who's now an associate professor at University of Colorado Boulder. And this so coincidentally happened to be the Baltimore metro area, being UMBC, that's near our location. And so the whole 6-county area, the square is her domain. And so she was interested in, ultimately we're connecting this to a urban growth model. And so she was looking at scenarios and how they would propagate into the future. But I just want to show you some snapshots of the work. So when we populate this model with our data, and then we generate the stream flow, what you'll see is what I'm showing here on the right is you can see the streams develop. So we initially drape the water table as an initial condition, some depth below the land surface, and then as the model is spun up, the water table rises in the valleys and drops in the hills, and you end up then water fills up the streams. You get stream flow, and we always want to ensure that the domain is draining, that water doesn't back up. And so we do various tests in the beginning. This was actually a drainage test slide, not a spin up slide. But that's the kind of that we generate the streams through the topography and then the model solving for the mass momentum conservation equations for water flow through the surface and subsurface. So in this particular case, there are many different kinds of data sets that we incorporate, and this is just to give you an idea how heterogeneous some of the data sets are. So we have the natural systems, soil hydraulic conductivity, bedrock hydraulic conductivity, soil and saprolite thickness. On the left is shown a cut of what ODD assimilated into the model, because the Baltimore crosses between the Piedmont physiographic province, the Atlantic coastal plain. So in the Piedmont, we have soil, saprolite, fractured rock. Atlantic coastal plain, we have a system of aquifers and aquatards. So she used the USGS database and assimilated this all into the model. So, with the hydraulic conductivity, you would have that even in a forested area, right? And so what we were doing is importing some version of what we could model as anthropogenic perturbation. So one thing Aditi was interested in is how water supply pipe leakage provides an additional source of recharge to groundwater, and or an additional source past rain. How lawn irrigation in summertime is affects recharge, and of course, the vegetative cover and impervious surfaces, are going to affect where water goes into the system. Okay, so it's the impervious surface coverage DEM, or the impervious surface coverage GIS layer is important, and we assign impervious surfaces a specific hydraulic conductivity. I mean, they're not zero, it's something small. So we assign those that are on top of the soil a limited hydraulic conductivity. So an example of some of the kind of output that's can be generated by the model is as follows. So Aditi put all this data in, spun up the model, and ran it. And what this is showing is the output in terms of subsurface storage. Okay, now that may seem foreign to you guys. You might be thinking, oh, what about depth of the groundwater? Subsurface storage is the volume in storage divided by the area, the area of the domain, to give you some kind of depth. And so you could think of this as like depth to water. So what's shown on this graph at the top are the bars of precipitation. And as we know, Baltimore is fairly wet throughout the year. And then the subsurface storage, which is expressed as a depth for reasons I just explained, you can see that it's a peak in April. And we all know, well, we should know, as hydrologists, aquifers fill up during the winter. Okay, so you usually see a peak in late spring. I'm sorry, in early spring. And then as you have leaf out, which is around April 10th around here, you see a gradual decline in subsurface storage, usually with the greatest decline being by the end of October, where we have senescence and the leaves fall off the trees, and then the aquifers start to fill up again. So when we see a result like this, we think, okay, well, that makes sense physically. We don't have validation data to a great extent. We do have some water well depths, but there's a real dearth of wells in the region. So that's the base case subsurface storage with all these anthropogenic perturbations going on. So this is kind of a busy graph, but what Aditi was interested in is if she, vegetated everywhere, or, took impervious surface off and just had natural hydraulic conductivities and, got rid of anthropogenic perturbations, how did that change the subsurface storage? So in this graph, this is the percent difference in subsurface storage between the base case scenario divided by precipitation minus evapotranspiration. So P minus ET would be the natural inputs and outputs. So she scaled by that. And so the only message that I want to talk about here, because I want to move on, is the black line is the base case and smashed and rescaled from the previous slide. And so what she showed, just when she removed all these anthropogenic inputs and outputs, all the pumping around and leaking pipes as we had modeled them, you generally saw an increase in subsurface storage. So basically that would say that these anthropogenic, this is the weighting of the anthropogenic inputs versus outputs. And if we shut them all off, you see an increase in subsurface storage. So that's kind of interesting because people make all kinds of arguments about whether, impervious area, completely blocks recharge, or you've got focused recharge in, cracks in impervious area. So anyway, this was a regional scale model. She also looked at the spatial distribution of these attributes, and I'm not going to talk about those here. You can take a look at the paper. So that's one regional scale example of an application of par flow. We were trying to address, ultimately, we were trying to model the existing system, and then we were projecting the system into the future to couple with an urban growth model to say how some of these features, how some of the responses may change. Okay, so going down to the small watershed scale. So this is the whole metropolitan region here. We work a lot with the Baltimore ecosystem study in the Gwynns Falls, which is shown here on the right. Two subwatersheds of the Gwynns Falls are Red Run and Dead Run. And so we are looking at small watersheds within Red Run and Dead Run, with the attributes being a variation in impervious surface area, amount, and pattern. And so the reason we've worked for so long in the Gwynns Falls is we go from a rural to urban gradient of development And so we've really milked that for all it's worth with a lot of sampling and analysis and many projects over the years. So this is one project where we're doing some groundwater modeling to look at the effects of this urban gradient on subsurface storage. So each of these subwatersheds we chose, and the surrounding domain was on the order of 1 to 2-ish square kilometers. And the main attribute is the fraction of impervious surface area differs as you go from Sunnydale up here in the hinterlands down to I guess the most developed down here was these Kevsway watershed, which was 70% impervious. So at any rate, what you can see here, the green is vegetation, the blue are streams, the purple is impervious area. And aside from the black solid fat lines, black is also impervious area. And then red is impervious area too. It's like buildings, okay? And so you can see as you go down this gradient, you can see, massively impervious area. But you can see the patterns change as we moved down the gradient. So Mike Barnes was the primary author on this work. He was a staff member here at UMBC. And so I'll just show you some example output. So he simulated 4 years of subsurface flow using Parflow CLM. And what he found was kind of interesting. So this is mean removed subsurface storage. So again, remember how I define subsurface storage. You can kind of think about it as aquifer levels. And what was really interesting, so this is mean removed. So this is showing the fluctuations over the course of 4 years. And so the first lesson is there's a great degree of interannual variability. You can see the precipitation up at the top. That may not look so variable. 2014 was a pretty wet year, but you can see the interannual variability, which is why in long-term, analyses that we're all beating the drum about in Baltimore ecosystem study, we try to look at long-term data because you see this interannual variability. So what is interesting here is that the highs, the greatest increase in subsurface storage and the greatest decrease in subsurface storage is at the watersheds that have the least amount of impervious surface area. In other words, they have more ground open to the atmosphere for infiltration, as opposed to the red, which is Kevsway, 70% impervious, and that has the lowest swings in subsurface storage. So you see this dampening, and you also see that the effect is greatest for long periods of dry and long periods of wet. And you also see that there is kind of a lag. If you look at this area here in the middle, you see this, drying down of the most rural area, and you see that the pattern follows by Kevsway. But you see, like the lowest low is delayed. There's kind of a lag here, and then when you wet up, you see all these kind of wet up at the same time together. So you see a much greater effect for the longer period of the weather perturbation, whereas for some of these smaller events, you see like these look like they're all right on top of each other. So we thought that was kind of interesting. What we ended up graphing here is the percent impervious area of these sub-watersheds, these little watersheds, versus the standard deviation of hourly subsurface storage. So that would be, the standard deviation of the graph I just showed you. And what this just shows is that there seems to be some kind of relationship between the percent impervious surface area and the subsurface storage, with the subsurface storage, the standard deviation being much greater in the rural watersheds. So you might think, well, there might be implications for solute storage from this kind of behavior. Okay, and we can make movies of this. So one thing that's kind of interesting here, if you're interested in exploring, is they're wetting up the Sunnydale region. And what you can see here over on this edge, you can see infiltration happening, if you can see my cursor, vertically, and then in the pervious area. And then it spreads laterally under the impervious areas because it can't evaporate. You can't get that kind of result with a model that only has 1D infiltration. Like you need 3D to be able to see that. So you can explore the 3D effects with this kind of model. Okay, so just quickly, the last example I have here is an EcoSlim example where we've taken the Parflow velocity, saturation, and porosity fields and run them through this advective, dispersive, diffusive Lagrangian particle transport code. So this code is kept by Reed Maxwell at Princeton, a recent publication in 2019. And from this model, we can calculate subsurface flow paths and travel times. So our problem of interest was as follows. For our field crew, we do a lot of water quality sampling. And one of our most interesting, revealing kinds of sampling we do is called synoptic sampling. And synoptic sampling is where you march up the stream over a finite period of time. You collect samples at a particular distance apart. So these were all 50 meters apart. You do this quickly. We can sample 6 kilometers in 5 hours. And we typically do this after a period of no rain, like 5 to 10 days of no rain, because there's no wastewater treatment going in, effluent going into this stream, dead run. And therefore, the stream is comprised of base flow, and base flow comes from groundwater. So if we look at this kind of sampling as a window into the spatially variable water quality, this kind of a steady bleeding of legacy reservoirs of chemicals into the stream, we see that when we repeat the synoptic sampling over and over and over again, we get the same result. So those dots are the average of 7 sampling. The little lines are the individual synoptics. So what we were interested in is seeing if we could use the model to maybe say something about where some of these chemicals might be coming from. So this is work that was done for this paper, which was published this past year by Madad Taleppour, who's a PhD, postdoc working at Johns Hopkins with Ben Zaitchik and company. And so he ran this 14 square kilometer watershed dead run through Parflow. And then he put particles in along the stream here at our sampling locations, doing this with a model, and track those backward to the landscape to get 2 things. We wanted to get the flow path length, this is the subsurface, and we wanted to get the land cover and land use at the exit points of these particles. So this map is a 2-dimensional rendering of 3-dimensional flow paths. They're fully 3-dimensional. And one thing that's really interesting when you look at this is how spatially variable those flow path lengths are. So, and it's dictated to some extent by the topography. So here in the middle of the domain, it's very flat. It's been plowed and bulldozed flat. And so the slopes the land slopes are gradual. It's interesting because the highways here, the interstates are up in the air. They have nothing to do with these flow paths. Okay, these are subsurface flow paths. So it's kind of dramatic to see how variable the flow path lengths are. So anyway, what we did with this data is that we looked at the cross correlation between the chemical signature and the urban feature at the exit point. So you do backward particle tracking to find the exit points, and then when you're obviously the water's going to go in, that's the entrance point for water. So so this is a blow up of that nice diagram with Amada. So what we were doing is we were looking at cross covariance of these particular chemicals, chloride, sulfate, nitrate, fluoride, with impervious surface area, sanitary sewer density, fill, meaning cut and fill as in fill in the urban landscape when bringing fill and stomp it down to build buildings on, and potable water pipe density. So, this cross covariance goes from minus to +1, and you can see the graphs here. And so, positive number is a positive correlation. So we see a pretty strong correlation between chloride impervious surfaces, as we do with sulfate impervious surfaces. And you can go on down here. Nitrate, just a little bit of positive correlation with impervious. We were expecting to see maybe more. We have leaking sewers in that region, maybe a little bit more correlation with sewers, which we did not see. For fluoride, which is a constituent of potable water, we in fact do see a positive correlation with the potable water pipes density. And also you might expect fluoride in sewage water when we have sewer leaks, because you flush your potable water and it gets into the sewer. So you can take a look at the paper if you want to get more insight. For impervious surfaces, if you're putting salt all over a parking lot in the winter and the parking lot's cracked, you would expect a lot of the chloride goes straight into the parking lot, underneath the parking lot, or run off to the edges of the parking lot and into the soil and underneath. And so we think that we have legacy pockets of contamination of some of these chemicals that are just gradually and consistently bleeding out into the stream over time. And so our ultimate goal is to be able to try to figure out where those pockets are. And we have other constituents we're looking at now. So anyway, those are just some examples of how the model can be used. And so at this point, I want to end and turn things over to Larry.
Oh, you're on mute, Larry.
Ah, so unmute. There we go.
There, we hear you now. Thank you.
You could hear me now. Okay, great. Thanks. So ParFlow was developed initially as a groundwater model. RESIS was developed really as a carbon budget model. It was funded by NASA Ecosystem Science, was jointly developed by Steve Running's group in Montana and my group in Toronto. And after we learned how to extract leaf area and vegetation type using thematic mapper at the unprecedented scale of 30 meters, we decided we wanted to see what the effective variable soil moisture was and microclimate on rates of photosynthesis, carbon sequestration, and cycling. So RESIS is essentially a joint hill slope scale to watershed scale, water, carbon, and then nitrogen processing model. So let's move down. And at the catchment scale, the assumption is that everything we're watching can vary significantly from a ridge, which is drier, down to a riparian area, which is much wetter. So you essentially get the subsidy and movement of both water and solutes down these types of gradients. So it was based initially on a marriage of biome BGC and a distributed hydrologic routing model. And you can see here the carbon component here on the left-hand side, matching the water cycle component over here as well. There's another nitrogen cycling that I won't talk about right now, but will become quite important as we get into both humid, where it's not water limited, and urban areas. Compared to ParFlow, it's an intermediate level of complexity, means that it will run faster, so we could run a much larger number of realizations to explore uncertainty space, and then trade-offs between different state and flux variables. For a high elevation and a low elevation site, this is now in the Coweta long-term ecological research site in the Southern Appalachians. We're showing both the observed discharge and then also the uncertainty space for that. Now, we also can observe the soil moisture over a long period of time from TDR in different locations on the hill slope. So in other words, ridge, which is 118, down to the riparian area, 218. And so we could get this trade-off of how well the calibration fit both discharge and the spatial distribution of soil moisture. The model is calibrated solely on soil and subsurface hydraulic variables, but includes a set of biogeochemical linked carbon and nitrogen cycling that is completely uncalibrated. So we calibrate for water. We have a number of observables in the nitrogen and carbon area, including some other uncalibrated areas, other data that we may not be using to calibrate on the hydrological side. So that's the model in brief as we applied it first to unurbanized areas. Then we move into the neighborhood. We build houses, pipes, roads, and everything that Claire spoke about: pipe flow, pipe leakage, pipe inflow and infiltration, addition of fertilizer, irrigation, potentially pesticides, personal care products, and so forth. We need to incorporate. So we're essentially translating a less managed watershed hydrologic biogeochemistry model into an urban area and running it at scales where the individual ecosystem patches. So the ecosystem model is solved at the subhill slope scale, so we could resolve ridge to stream differences. So we could solve that at levels that are amenable to human decision making. Each household will add a certain amount of fertilizer or irrigate or maintain a certain amount of lawn and so forth. So we spent a lot of time knocking on lots of doors in the Baltimore area to try to tease out how much and when people fertilize, how much and when they irrigate, and so forth. And as you could imagine, if somebody knocked on your door and asked you, so how many kilograms of nitrogen per hectare? We don't ask that question, but we try to tease that out from the products that they're using, maybe contracting with lawn care companies and so forth, so we could get an estimate of that. We have to include infrastructure. So in the 1980s around Baltimore, in this case, this is in Chapel Hill, there was detention ponds was the big stormwater control feature. So incorporating the effect of peak shaving and storage and slow release by detention store ponds in urban areas was something we needed to incorporate. Now let's move into Baltimore. And so we're looking first at our exurban watershed. That is Basements Run. It's up off of around Cockeysville, a little bit west of Cockeysville, west of 83. It's 2/3 forest and county park with a couple of regional gas line cuts that bring natural gas from Louisiana up to the northeast. And suburban, low density suburban on septic and on individual groundwater wells. These are in water supply catchments. I think Darren's house might be shown in this picture, and it's 2 acre zoning to protect the watersheds themselves. So once again, we calibrate for hydrology. I'll point out we're not getting all these low flows, but this is down less than 0.5 millimeter a day. So it's a fairly small amount of the total budget. And then we simulate without calibration the biogeochemistry. So full nitrogen cycle and full carbon cycle. This is just what's coming out of the streams, and we've been monitoring as part of the Baltimore ecosystem study. Stream over here, Pond Branch, and then Basements Run at the gauge down here since 1998. So we have uncertainty. We're just showing the peak Nash Sutcliffe efficiency model for nitrate in the blue, which is under predicting. But if we look at the full 95% confidence intervals, by looking at all behavioral parameter sets, in other words, all the sets that are giving us reasonable flows, then we find at daily to weekly to monthly levels, we're capturing the dynamics reasonably for nitrogen concentrations and loads. Loads will actually be better because they include they're multiplied by the discharge. This is quite important because in Baltimore has been under consent decree to reduce the amount of nitrate going into the bay, and in this case, into drinking water reservoirs. What we're finding typically through the BES and through our modeling is the peak nitrogen load per unit area comes out of these types of landscapes, septic served, low density landscapes rather than the dense urban sites. So that was time series. This is spatial series from 2001 up to 2017. This is the carbon budget. Well, a portion of the carbon budget, the net photosynthesis. We could map out different forms of respiration, maintenance, and heterogeneous respiration. The model will grow the canopy by allocation of the net photosynthate to different parts of the plants, crops, forest, lawn. And we put in different types of human management, mowing regimes, fertilization regimes, irrigation regimes, and so forth. That's net photosynthesis. This is then denitrification. The nitrate is added here in the suburban area through septic systems, leaking septic systems, and lawn fertilization. And when it hits wet areas further down the flow paths, the groundwater flow paths, we're getting a greater amount of denitrification, of course, peaking in summer and around the time of fertilization, minimized in the winter when it's temperature limited. So down here, we're actually resolving down at the parcel level and looking. This would be the level at which we would seek to put in BMPs and different methods to control these loads. Move further into the urban area, and this is just repeating what Claire stated. We have we have at least 3 different sets of networks of pipes. We have potable water pipes that leak to an extent. We have stormwater pipes. Baltimore and Baltimore County have separate stormwater and sanitary sewers. And the sanitary sewers, although they're designed to be separate from the natural environment, as Claire and Aditi have shown, could actually absorb a substantial amount of groundwater inflow and surface inflow and infiltration. Some of the numbers are actually quite surprising, but seem to be fairly common. Up to 30% of the rainfall may be disappearing down these pipes. Lower than that in most areas, but that's something we need to be able to handle. So we put in a series of different BMPs. This is a stub out swale drain. So there's a series of baffles to create detention store. There's cuts in the curbs to route stormwater flow off of the roads into these baffles, which overflow. Then there should be some sort of a tall vegetation to transpire. We resolve through the model, still model conductivity, responding to environment, atmospheric and soil water conditions and species level conditions. That will reduce the amount of soil saturation, as Claire was mentioning, between storms themselves. So we want to be able to incorporate this. An initial attempt to do this was done in Scott's Level Branch. This is from a paper that Roy Zhang published last year. Scott's Level Branch is 8 square kilometers. It's inner suburbs in the county. Medium density housing on sanitary sewers and city water. We chose this area because there's been extensive stream restoration carried out in different portions of this area. And then we're showing the simulated stream flow, and then the simulated nitrate with some observations as well. What we're interested in doing is specifying a series of different types of GI, green infrastructure, down at the parcel or small hill slope scale. So this is a status quo current conditions, similar to what Claire was showing at very high resolution. Excuse me. This is replacing lawn or grass with trees, with exception of a 10-meter buffer between housing, so people can retain their lawns. There's extensive areas of lawns are pulled out. Roadside bioswales, these areas on the side of the roads. So we're essentially putting in stub outs and putting in taller vegetation in these areas that'll absorb road runoff. And then in the low intensity streets, putting in permeable pavements. So these are changes in the distribution, going the wrong direction, of denitrification. Urban forest, this reforestation here, actually reduces the amount of denitrification because it's reducing surface saturations. The trees are transpiring to a much greater extent. Roadside bioswales increase denitrification because they're saturating those areas from run-on infiltration. Permeable roads permeable pavements are increasing and causing groundwater mounding, just like the roadside bioswales. So those areas are also increasing denitrification. Changes in vegetation uptake, roadside bioswales and pavement, permeable pavement, of course, do just about nothing. Where you have some urban reforestation, those extensive areas of lawns that are being reforested are increasing nitrogen uptake by vegetation. So you're getting some stormwater controls or water quality benefits from that. Let me end with Stony Run, which we've just been starting to work with interest from the city. Let's see, Scott's Level Branch is 8 square kilometers. We're simulating this, I think, at about, Roy could tell us, but I think at about 15 meters. By the way, those grid cells can have multiple forms of land cover. Walk out your door, you have a meter wide path, you have a little bit of lawn, you have a street, you have a more extensive lawn or rubble, and then a rooftop. So within 15 meters, you have a lot of different types of surface covers. So this is subgrid variability in the surface cover that may be sharing a soil resource. Stony Run, similar and older development. Scott's Level built out in the 60s or so. The 70s, this is built out, I'm going to guess 10s to 20s or so. So older infrastructure here in general. Those of you who are sitting in Johns Hopkins, I think you're just a little bit south of here, but you could lean out your window and wave at this point. About 45% canopy. It's already fairly forested. 13% lawns, 24% impervious areas. It has more canopy actually than Scotts Level Branch. If we take that roadside bioswale, those types of stub outs, narrow areas, replace lawn, replace a certain amount of road with these detention store bioswales that absorb road runoff. This is the change in detention store that we're seeing over those areas. We do have some negative areas because this is road runoff that's being absorbed and not delivered to some other areas. This is a change in root zone storage in those bioswales. This is a change in evapotranspiration in those bioswales. In the winter, this is 0 or so. During the summer, during drier periods, this could get to be larger, and we could then turn this into a change in the runoff production and stream flow that's occurring. So this is the simulated, observed and simulated. We're not using local precipitation. I think we're using sourced largely from BWI, so it's a little bit distance, and we may be missing a set of large convectional storms or making errors of commission of large convectional storms in the summertime. What's more important is the differences in the stream flow and the amount of stream flow over this longer period of time that we're getting from roadside bioswales, by urban reforestation, and by the combination of both. So those are the areas we're working with. Once again, all of these are working with engineered flow paths for routing water either off of rooftops or off of roads into permeable areas or different types of green infrastructure. I think that's about as far as I'll go. The last one was we do see some bias in these simulations because we're not handling the potentially large amount of sewer infiltration. Larger flows above 1 millimeter a day, which is a medium to low runoff amount, are reasonably arrayed along this 1-to-1 line. We have bias below that, and we think that's because we're seeing high winter base flows when groundwater tables are high. In other words, in this sort of situation, we're not simulating the loss of water down those sanitary sewer pipes. That's actually being delivered to the treatment center itself. We've been incorporating an inflow and infiltration model drawn from a couple of other sources to try to be able to simulate when we're getting sewer infiltration and exfiltration. Exfiltration when the groundwater table is low and it's yielding effluent out into the groundwater, and inflows when groundwater is high. City has been putting a lot of effort and a lot of money in the consent decree to reducing this amount. Claire showed ADITI simulations where what would happen if you cut out all of the infiltration, and there's actually a substantial effect of that on the storage and potentially on the groundwater outflow and even potentially on stream flow. So let's finish so we have some time to talk. Both of these sets of models that we've shown do not incorporate the detailed hydraulic routing. In other words, solving of the full St. Venant equations, as Claire was mentioning at the outset, that are important for routing runoff in pipe flow, backwater effects, or for full flood extent. In other words, overflow from the streamlines or sewer surcharging. Other groups, other people in the project are working with SWIM 2D, PC SWIM that include a two-dimensional surface water flow. The city is using InfoWorks, ICM. Both of these sets of models are proprietary. We haven't really discussed whether we want to try to stick within this project open source simulation, open source software, so it could be distributed. We're also working with HECRAS 2D, which is in HECRAS 6.4, which will provide us the ability to do this type of routing. And Claire mentioned Julia is working with CityCat, and there's also a model called ListFlood we might think of, but I think we would like to hear more about SWIM, InfoWorks, and CityCat at some point in this series. So I think that's it. Let me end and leave at least 10 minutes or so or more for discussion. So questions for either of us? So I'll point out that a good deal of the nitrogen and the carbon component of rhesus has a common ancestor with ELM. It's somewhat simplified at this point compared to what's sitting in ELM, but has the ability to resolve the hill slope hydrology and the fairly detailed delivery of moisture from either pipe flow or runoff infiltration, which becomes the key to green infrastructure design.
Thanks so much, Larry and Clara. Maybe I should kick off with a question building on your closing slide there, right? And so one thing we know that the water team has been wrangling is all of these different models, right? And that they have different strengths and they're useful for different purposes. I could absolutely see using different models for different BSEC applications. And then there's this discussion about pulling them together, right? Leveraging capabilities in ELM and rhesus and trying to incorporate them to other models. And I'm wondering, what are your thoughts on that? It's something that we, highlighted in the proposal, right? Because that's what one does in a proposal, right? Talks about building integrated systems. But right now, are you seeing any opportunities or barriers or reasons to rethink how we bring these different models together?
So I think what we've discussed is starting to work around the flux towers and maybe in some of our small gauged watersheds to run all models side by side. And then to see what's the actual impact. I mean, is the impact of redistributing soil moisture negligible, or does it become important when averaged over that for the average flux and stores in those areas? So can we find a way, if there is bias, to do bias correction? We're not going to run rhesus at the full metropolitan area. We could run ELM at the full metropolitan area, but we want to know, when does bias creep in? When are there methods to actually correct there? Are there methods of averaging the input parameters? And we have to sit down and go side by side. So what are in our ecophysiological parameter sets that are similar? What's different? How do we translate those with different levels of heterogeneity? Let's see, Ken is asking, do the higher fidelity models as data tested truth to evaluate the simpler models? So I remember when I was working with Steve Running, and he would test remote sensing methods and he would refer to the model as the truth. We're testing models with models. So we really have to have observables. But because we could tie these higher fidelity models to field scale measurements, it's really difficult to measure what's soil moisture at 1 kilometer. We can, however, measure it at these finer resolutions. And the reason for running these high fidelity models is so we could compare modeled with measured values. So that's the idea. So I hesitate to call the high fidelity models truth, because even though we data test them, they'll still have their bias, but that's the idea. Can we see when the more aggregated models may be showing symptomatic bias? But the advantage is the flux towers will do aggregate over those types of footprints, but we may be able to diagnose if one set of models is varying from the flux towers. Is it due to soil moisture or an inappropriate response to vapor pressure deficits or some other type of problem? Other questions or discussion? So you can see why getting some of these soil measurements are fairly critical. We work in areas outside the city where Sergo data is at least reasonable. We're taking the spatial distribution of our key hydraulic parameters and we're using transfer functions to upscale those. Sergo doesn't really work in cities, so more detailed sampling of soil hydraulics in those areas, I think, is going to be critical to understanding.
Yeah, when we think about it, Larry, I mean, it's something I know that's come up often in theme team meetings and even proposal planning are the different units of aggregation, right? So we've got the flux tower footprint. It's gonna help us with obviously hopefully fluxes. And then we've got the watersheds. And so when you think about the strategy for sampling soils and other quantities relevant to the modeling, how do we reconcile that? Like, do we need to, is the sampling plan watershed based? Are we taking subsets of watersheds in order to align with the flux towers or what?
Yeah, so I don't think we are putting flux towers where we have small gauge catchments. The closest might be what's in Howard Park, which is at least very close to where the powder mill gauge used to be. But we could calibrate a model, using discharge data and then see how it's performing with the flux tower information. So we're going to have one larger set, and then we need to have some of these distributed measurements. Claire mentioned doing synoptic sampling as an example, up and down some of the streams. We do this for terrestrial, for land surface types as well. We repeat soil moisture surveys at different times during wet, dry, growing season, non-growing season to see, can we replicate these types of patterns for the high fidelity models? And are we able to gain the aggregated flux in those areas? ELM can be run at higher resolution. We can run at similar resolutions. That's just kind of controlling for the presence or absence of the lateral moisture redistribution. Dan is asking, rhesus track nutrient cycling in vegetation? Yes. So there's a full nitrogen. We don't really do phosphorus. We're assuming most of this vegetation is nitrogen limited, but it will use, and I presume I think it's a very similar nitrogen cycle to what's sitting in ELM, joint carbon and nitrogen cycle. The last part is, and this is something that Peter brought up in our discussion recently, actually yesterday in the BES meetings, urban areas tend to be very biodiverse because of all the introduced species. This area is very biodiverse. How do we represent urban vegetation as well? So what's the level at which we have to differentiate between different types of vegetation physiology? That's something that's going to be a smaller group talking about. How does ELM do it at this point? What's adopted in rhesus? What's being used in other cases? Differences in stomatal connectivity, differences in nutrient cycling, and so forth. I don't think that Megan is on the call, but this was some of the questions about the sampling of different types of vegetation types.
And there you see Dan's question in the chat about tracking nutrient cycling.
Yeah, so that's what I was referring to. So
okay,
we'll compare. So what stores are sitting in the vegetation in rhesus and in ELM? Both of them do an allocation and a growth over time. Because they have common ancestors, we just need to sit down with those two tables and see what's the same, what's different. So Ken is suggesting we simply arrange a model into comparison program. We could start that before we start generating tower flux data. That's going to be a year or two, maybe. We'll start seeing streaming taking place before. My experience with setting up new flux towers is there's always correction cycles that go on. But can start just comparing in between them in an uncalibrated mode. We'd have to make sure we're using similar types of soil, similar types of vegetation, similar types of land cover, and then run through them.
All right. I see we're pretty much at time here. So maybe we can stop there and obviously continue these conversations as we go. Thank you so much, Claire and Larry. This was great. Great education during the talk and great resource to have this talk and those slides that we'll have on the website because really great overview of what we've got going on in the water and water quality modeling world here. And Ken has pointed out now in the chat, that'd be good to get an archive going in these publications. That's good, Ken. Let's make that an action item for BSEC more broadly.
Yeah. Do we have a pubs location on our Google Drive in general? And should we just break out a separate folder, Mac, that shows presentation referred to?
One thing that there is there's a Zotero, a shared Zotero library for BSEC, which each theme team has a full subfolder in.
Okay.
So that might be, I mean, the drive is nice because you actually have the papers right there, but the Zotero makes it searchable and organized. So
Right. I think the Zotero is a good idea.
okay.
Do us a favor or do me a favor and just send around the information about accessing that.
Cool. Mac, did you set that one up, Mac? I can't remember who set it up.
I did not, but I'll take a look around for it.
We'll figure it out. We'll find the responsible party.
Yeah.
Oh, you did? Okay.
Let me say one more thing. We gather a lot of information from homeowners on their fertilizer use. Homeowners don't know how much fertilizer they use. I bet Farmer Trippy knows how much fertilizer he actually uses and what he's growing and how much he's yielding and so forth. So actually working with some urban farmers know what they're using. It's a cost basis for them. It's operational expenses and methods. So besides working at the sort of the parcel, the residential parcel, getting an idea as to transferring these models and trying them out in some of these urban farms where there's a lot more known would be great.
On that note of collaboration, let's call it. So thanks again, everybody, and we'll be in touch soon.
See
Take
you,
care.
everybody.
Bye.